All right, good morning, everybody. Um, let's continue our study regarding acids and bases, and more specifically, let's tackle the acid-base reactions, and then we can move on to the next thing. Okay, so I want to do a quick recap here, because maybe I was not very clear last time. Seems like some people are having trouble regarding when we have the molecular form and the ionic form. So let's do one thing here. Okay, so let me go back here to the definition of a base according to Arrhenius. So according to Arrhenius, base is any substance that produces OH minus ions when dissolved in water, okay? So let's go back to our example here regarding sodium hydroxide. Okay, so sodium hydroxide at room temperature is a solid. And when sodium hydroxide is a solid, that form here is called molecular form. Okay, so let's get here. Okay. To show you that I'm not lying, so this would be sodium hydroxide at room temperature. So it's a solid, and that is called the molecular form. And then when we add water, so the process here is going to be a little bit slow because it's a big chunk. So let's add water. Let's leave here on the side. So the fact that you dissolved sodium hydroxide in water, according to the Arrhenius definition, water is going to be strong enough to break up the interaction between sodium and hydroxyl ions, and that's going to produce ions that are dissolved in water. Okay, sodium plus, now dissolved in water, and hydroxyl dissolved in water. Okay, so water is going to break up the interaction between these two ions that's very strong in the solid. And then when we have Na plus and OH minus in water, that here is called ionic form. That's why we have the molecular equation and the ionic equations. They represent the same thing in a slightly different way. Okay, so the pellet here is dissolving. So it's getting here more soluble. And then it's basically a clear solution, okay? So the fact that it's a clear solution is because we have now ions in solution and not the molecular form. And the same thing, slightly the same thing for acids, okay? HCl at room temperature, this is a gas. And again, this is called molecular form. When we dissolve HCl in water, according to the Arrhenius definition, water is going to break up the bond between hydrogen and chlorine, and that is always going to produce H plus whatever is left with the negative charge. Okay, so HCl dissolved in water, you actually don't have HCl anymore, but you have H plus and Cl minus, and therefore This is now called the ionic form. Okay, so that's why we need to represent molecular equations and ionic equations. Okay, so remember that any acid in water is going to release H plus ions and generate an anion which is composed by whatever was left in the formula. Okay, so let me go back to the definition of bases, and I can give you time to take notes. Okay, so here the base, I did the same thing here at the bottom. Sodium hydroxide, for example, solid at room temperature. When we dissolve any base in water, that's going to release OH minus, because that's the definition of a base, and then generate the cations that are composed by whatever is left in the formula of the base. So every time I'm talking about the molecular equations, that is the form that I'm going to use. And when I'm talking about the ionic equations, no matter if it is the overall or net ionic, I have to consider what are the ions dissolved in the solution. Okay, so with that, then we can start looking at the acid-base reactions. The products are always going to be a salt and water, okay? So let's start, we started here with the hydrochloric acid and sodium hydroxide examples. So let's first start again with the molecular equation. Remember, the molecular equation, we are not going to consider any sort of ions. So we are going to write the compounds in the molecular form. Acid-base reactions is a double displacement reaction. Hydrogen is going to combine with OH, forming water, and sodium is going to combine with chlorine, forming the salt. Okay, sodium chloride. That's how the reactions between acids and bases work out. And then at the end, we also discussed about the solubility of the salt. Okay, to determine the solubility of the salt, you are going to either look at the positive part or the negative part. It does not matter, okay? Whatever you find in the table, it is what's going to determine the solubility of the salt. So let's look here, sodium chloride, okay? So we have here sodium plus, which is group 1, or we have Cl minus, which is group 17. So let's see what we are going to find in the solubility table, and that's going to be enough to determine the solubility. Okay, we just need half of the components here to determine the solubility. Okay, so going back to the table, the first row right here is group 1. Okay, any salt from group 1 is soluble, and there are no exceptions. If you want to look at the chloride part, you go here to the 4th row, and you find chloride here as well. So if you want to look at the chloride, I don't care. You can look at the chloride. Chloride salts are always soluble with the exception of silver, lead, and mercury salts. Sodium chloride is not the exception, therefore is soluble. So no matter if you look at the cation or the anion, they have to tell you the same thing, okay? And you just need either the cation or the anion to determine the solubility. Which one you are going to pick? It depends on the case. It is whatever it's in the table. And this table will cover all the cases that we are going to work. So therefore, according to the table, sodium chloride is a soluble salt. Okay, so we don't have to indicate that a precipitate is forming. Now, what's the difference between the molecular equation and the ionic equations? Now, we are going to represent how the compounds are dissolved in water and use the ions to draw the equation. So let's start with the overall ionic equation. So we have here HCl. The first thing that I like to do is to dissolve HCl in water to figure out what are the ions that are going to be formed. Again, the bond here is going to be broken. So we have H plus. Because now this ion is dissolved in water, we must indicate AQ here. And the counterpart that is formed is Cl minus. And this is dissolved in water as well. And then we are going to indicate AQ. Okay, so the original compound HCl, of course, does not have H plus and Cl minus, but those ions are formed once the compound is dissolved in water, and we want to represent the ions that are formed. That's the idea of ionic equations. And we do the same thing with the base because we need to know what are the ions that are participating. So we have here sodium hydroxide that's going to be dissolved in water. Water is going to break the interaction between sodium and hydroxyl, producing sodium plus, now dissolved in water, and OH minus, again dissolved in water. Okay, so now that you have all the ions from the reagents, the next step is to combine those ions to generate products. Of course, there is low probability of a positive ion combining with a positive ion because of repulsion. Therefore, it is more probable that a positive ion is going to combine with a negative ion. And that's the reason that H plus is going to combine with OH minus. H plus plus OH minus, that's going to produce HOH, and that's simply water. And of course, is in the liquid state. The other positive ion in solution is then going to combine with Cl minus, okay? So they are going to attract each other. And again, when sodium plus combines with Cl minus, we have here two possibilities. Either a solid is going to be formed, an ACl, or they will stay soluble in solution as Na plus and Cl minus. Okay. How do I know which form is going to be preferred? If an ACl is not soluble, that's going to be the form preferred. If it is soluble, they will be as separated ions. And we all know that sodium chloride, right here, that's basically salt, is very soluble in water. Okay. So that's going to form a very nice solution when all the salt gets dissolved in water. If something is soluble in water, and we are talking about salt, what we are going to have in solution is basically the ions separated and not bonded together, okay? So that's the reason that we have here sodium plus AQ plus Cl minus AQ and not NaCl as one thing. Okay, so what we have here now, it's the overall ionic equation. Okay, so we have all the ions represented in the equation. And see here that we have Na plus and Cl minus in the beginning and at the end. So when you have the same ions in the beginning and at the end, we also call those ions as expectator ions. Okay, so they don't do anything. They are just watching the reaction proceed because the identity in the beginning is the same identity compared with the end. So the trick here when you are dealing with overall ionic equations is first dissolve the acid in water, producing H plus and an anion, okay? So let's do like a pre-reaction. The same thing for the base, always going to produce hydroxyl and a cation. Now that you know all the ions, you are going to combine positive with negative. One of the possible combinations is the formation of water, and the other possible combination is the formation of a salt. This salt may be soluble or not soluble. If it is not soluble, the cation and anion are going to combine and precipitate. If it is soluble, the ions will be kept in solution. How do you know when it's soluble or not soluble? Go to the solubility table and look at the case. You just need the cation or the anion, okay? Which one you are going to use, it depends on the situation. It depends on what you have in the reaction. Okay, so now that we have the overall ionic equation, the next step is the net ionic equation. in the net ionic equation, we are going to basically eliminate the expectator ions. How do we know what are the expectator ions? Is whatever ion shows up in the beginning and at the end unchanged. So let me rewrite here the overall ionic equation. So we have here H plus reacting with Cl minus, sorry, H plus Cl minus reacting with Na plus, OH minus producing Na plus, Cl minus, and water. Okay, so see here, Na plus shows up on both sides, Cl minus also on both sides. However, H plus only shows up in the reagent side because you have to find the identical compound on the other side. Therefore, we cannot cancel. So H plus is going to show up in the net ionic equation. And the same thing with OH minus. You have to have the identical compound on the other side, which is not the case. And then water is the only product. Okay, so the net ionic equation will only show the ions that are reacting de facto. Okay, so we are going to eliminate the expectator ions, and as expectator ions are the ions that show up in the reagent and in the product side. So that's how you move from the molecular equation to the overall ionic equation, and finally to the net ionic equation. Always make sure your reaction is balanced out, okay? Okay. So the second example I did with you guys was regarding the hydrofluoric acid and calcium hydroxide. Okay, so let's see here. We can revisit this example here. Okay, so again here, HF reacting with calcium hydroxide, it's going to produce salt and water. Okay, so remember that the hydrogen is going to combine with the hydroxyl, producing water right here, and calcium is going to combine with fluoride, producing CaF2. Attention with the charges to make sure you get the right formula for the salt. Okay, CaF2. So therefore, you need to balance this reaction out. So we are going to end up with 2 HFs and 2 waters, and then 1 calcium hydroxide and 1 calcium fluoride. So that's the molecular equation. Okay, so let's access here the solubility of calcium fluoride, because we know that this is the salt being formed. Okay, calcium fluoride is composed by calcium 2 plus which is from group 2, and fluoride. So we need to find one of those ions in the solubility table, and that is enough. So let's go all the way down to the solubility tables. Okay, so we don't have here anything for group 2. Therefore, the only option is to find the fluoride, and it is at the very bottom of the table. Fluoride salts are, in most of the cases, insoluble. The exception is group 1 and ammonium. Therefore, calcium fluoride formed by fluorides and group 2 must be insoluble, which means that this product here is a solid. Okay. Every time a solid is formed, we call that precipitate. Okay, so therefore, if you mix a solution of HF and calcium hydroxide, you are going to notice the formation of a solid. The identity of the solid is calcium fluoride, because this is an insoluble salt. Once you know the molecular equation, the ionic equation is going to tell you exactly the same thing, but it's going to represent reagents and products in the ionic form. The strategy here is to do a pre-reaction between acid and water and base and water. So we start here with HF. Every time an acid is dissolved in water, that's going to produce H+ ions and the respective counter ion. So we are going to break the bond between hydrogen and fluorine, producing H+ and F-. I added a number 2 here because that comes from the molecular equation, okay? So those are the stoichiometric coefficients that came from the molecular equation. So we are just going to use them to make things easier. And here the same thing for calcium hydroxide. So attention now that we have 2 hydroxyl ions. Therefore, when we dissolve this compound in water, we have to produce 2 hydroxide ions, and then calcium 2+. When calcium 2+ combines with fluoride, again, there are 2 options. They are either separated ions in solution if it is soluble, or they form such a strong bond that they become a solid. From the solubility tables, we know that calcium fluoride is a solid in solution. So that's why I'm representing calcium fluoride as CaF2, okay, and not Ca2+ plus 2F-. And I have to indicate here the physical state for calcium fluoride. Okay, so look here as well. So now that we have the overall ionic equation, the next step is to determine the net ionic equation. For the net ionic equation, we will cancel everything that shows up on the left side and on the right side. It has to be the identical, okay? Not similar, identical. Let's start with H+. you have H plus here, but no H plus on the other side, therefore it cannot be canceled. Fluoride, F minus. You don't have F minus on the right side, therefore it cannot be canceled. So that's why it's showing up in the net ionic equation. And the same thing for Ca2 plus. You don't have Ca2 plus by itself, okay? Ca is now combined with fluorine, therefore it cannot be canceled. And finally, OH minus, you don't have on both sides, it cannot be canceled as well. And that's why, in this case, the overall ionic equation is identical to the net ionic equation because we cannot cancel anything. All right, so the third example here is a more complex example. So we have here phosphoric acid reacting with barium hydroxide. Okay. Phosphoric acid is H3PO4, and that's going to react with barium hydroxide, BaOH2. So let's start with the molecular equation, as we already did here. So let's revisit that. So this is an acid-base reaction. You don't have to think too much here. It's always going to form water and a salt, okay? So the water is the result of the reaction between hydrogen and OH, and the salt is going to be formed by barium reacting with PO4. Barium and PO4. So now you have to pay a lot of attention here because barium is 2 plus and PO4 is 3 minus. So you need to remember that. Therefore, you need to cross charges, which means we are going to have 3 baryons for 2 phosphates in the structure of the compound. As you can see here, the reaction is unbalanced. So what I like to do is first look at the oxo anion, PO4. So we have 2 PO4s in the products. Therefore, we need to have 2 PO4 in the reagent. Okay, so this number 2 is multiplying this whole unit here, PO4. Now look at the barium. We have 3 baryons in the products. Therefore, we need to have 3 in the reagents. Okay. And there is always going to be a number 1 here for the salt. And now we balance the water. 6 hydrogens here. 3 times 2, 6 hydrogens there. So we need to have 12 hydrogens, which means we need to have 6 water molecules. Okay, so this is the molecular equation. And that's the first step to write any sort of acid-base reaction. Okay, so now let's write the overall ionic equation. So to write the overall ionic equation, the first step is a pre-reaction between acid and water, and also base and water. Okay, so be very careful here with oxoacids. Okay, so because the book follows a weird order, I cannot tell you right out of the bat that the structure of phosphoric acid is the one that I'm showing here on the top of the screen. What the water is going to do in this case is to break the bonds between hydrogen and oxygen. Okay, so what we are going to produce here is H plus and PO4 3 minus. Because you have 3 hydrogens bonded to the oxygens, we are going to produce 3H plus. Okay, so be very careful with that. Some people, they try to break the bond here and they produce H3 plus, which is something like that. And this is not right, okay? So what you are producing is H plus 3H plus, because the bond between hydrogen and oxygen is going to be broken here. So those are the products of this reaction between H3PO4 and water. Any base in water is going to produce OH minus. Because we have 2 here, we need to produce 2 over there. And the cation, okay? Barium 2 plus. For the overall ionic equation, you must indicate the physical state, always. Okay, so now that we know all the ions that are in solution, now we start combining positive with negative. Therefore, H plus is going to combine with OH minus. That's going to produce water in the liquid state. And then the other combination, the other possible combination is barium 2 plus with phosphate. Okay, so barium 2 plus with phosphate. Again, 2 options here. In water, they are just the separated ions in solution. And this is the case that the compound is soluble, or they form such a strong bond that they are going to precipitate and form a solid, okay? And this is when the salt is insoluble. How do I know that's soluble or insoluble? We are going to use the solubility table. And again, we just need the cation or the anion. That's going to be enough to determine the solubility. So let's go all the way down to the solubility table. Barium is from the group 2. We don't have group 2 in the solubility table. However, we have the other half of the salt, phosphate. And phosphate forms usually insoluble salts with the exception of group 1 and ammonium as cations. Barium does not belong to group 1, therefore barium phosphate must be an insoluble salt. Okay, so therefore that is the form that's going to show up in solution. Okay, we have such a strong bond between barium and phosphate that this compound is a solid. And of course, this reaction is unbalanced. So we need 3 baryons and 2 phosphates. And then what I like to do is to recycle the coefficients from the molecular equation. So we are going to generate 6 waters. Therefore, we have 12 hydrogens. Sorry, to count. We have 6 hydrogens here and 6 hydrogens from there, totaling 12. Okay, so if you simply use the coefficients that came from the molecular equation, then you are going to get the number right away. Okay, so that's the overall ionic equation. The net ionic equation is going to be obtained when you cancel the expectator ions. And again, if an ion shows up on the left and on the right identically, you may cancel, okay? If it's similar, that doesn't allow you to cancel out. H plus and OH minus, they will always form water, so they will never be canceled. So I'm not going to even lose my time with that. Phosphate shows up on the left, but does not show up by itself on the right side. Okay, so that doesn't mean that means you cannot cancel. Okay, phosphate here is now combined with barium. And then the same thing with barium. Shows up on the left, but does not show up as barium 2 plus on the right side. So nothing can be canceled. Therefore, the overall ionic equation is identical to the net ionic equation in this case. Okay. Always when you are writing ionic equations, you must represent the physical states for every component of the reaction. So in this case, when you are mixing a aqueous solution of phosphoric acid and barium hydroxide, after the mixing, you will notice a solid being formed in solution, and the identity of this solid is barium phosphate, okay? So this is also called precipitate, and we can abbreviate that by PPT. Okay, usually the reactions that they tend to form a solid to achieve stability, okay? So reactions tend to move in a direction of forming a solid or the other way around. If you have a solid, the reaction tends to move in a direction that solubilizes the solid. Okay? So you have to have a visual change in this case. Okay, so that's how you write molecular, overall ionic equations and net ionic equations when you have acids reacting with bases. The products are always going to be a salt and water. The molecular equation, you're going to consider the molecular form of the compounds, while the ionic equation, you are going to deal with the ions in solution. Both reactions represent the same thing in different ways, okay? So we are not changing anything. You have to pay attention to the formation of a precipitate. You are going to determine if there is a precipitate or not using the solubility tables. You don't have to find both parts of the salt in the solubility table. You either look for the cation or the anion, and pay attention to the exceptions. Okay, so you don't need to memorize the table. You can always refer back to the table. So that's going to be your supporting material. Okay, so I don't have time to start this, but that's going to be our goal on Monday. Now we are going to take a look at the reactions between salts, okay? A salt can react with another salt, forming different salts. The reaction between salts are also a double displacement sort of reaction. So that means the positive part of one salt is going to attract the negative part of the other salt, and vice versa. And then we are going to determine if one or more of the products are solids or not. And we are going to write the same thing. Molecular equation, we are just going to consider the molecular compounds, and overall and net ionic equation. And we are always going to refer to the solubility table to make sure we get the correct physical state of each compound in the equation. Okay, so with that being said, I think that's it for today. So I hope you have a good weekend, and I will see you on Monday.
Thank you, George. Have a good weekend.
Bye-bye.
Have a good
Have a nice birthday.
Thank you, Professor.
Bye-bye.